Hello, everyone. This is your friendly neighborhood physical chemistry video narrator, Dr. Hopkins, and we're presenting the last of our three videos on the hydrogen atom. In the last two, we looked at the solutions to the Hamiltonian, and then in the last video, we looked at the angular portion, which is something that we had solved from the rigid rotor. We applied that to the shapes of orbitals, kind of to build our common sense that we had from general chemistry. And in this case, we're going to look at the radial functions. And so you'll recall that the wave function split into two parts. We had the angular and the radial portion. And here I show two examples which I've written out for the 1s and the 2s orbitals. So the n equals 1, L equals 0, n equals 2, L equals 0 orbitals. So these are the radial distributed. These are probability amplitudes for the electron, the distance of the electron from the nucleus, the proton in this case. There are other examples that I don't remember exactly how many there are. On page 212 in your text, it's the section right above where they show the complete wave functions that have both the radial and the angular portion. And so if we go and we look at what do these mean, so they're just like any other wave function. They're just the radial part of the wave function. So the r is just the probability amplitude. R squared is our probability. So this is all from the definitions of quantum mechanics. But maybe the most useful, if we're interested in, okay, where is the location of the electron with respect to the nucleus, we really want to look at the radial distribution functions. And so that's basically the r squared. So the wave function squared, so our probability, times our volume element, r squared from the d tau that we get. If we plot that, that'll give our probable location of an electron in that particular orbital. And that's probably the most useful for chemistry. So let's show a couple plots. And here I have, on the left, I have a plot of the 1s and 2s radial distribution functions. On the right, we have the 2p, 3s, and 3p orbitals shown. You can see the x-axis has the radius in terms of Bohr radii, and then the y is the radial distribution. If we look at this, you'll notice that there are nodes, especially in the 2s. So once the 1s doesn't have a node, but in the 2s, 3s and 3s and 3p and so forth have nodes. These are radial nodes. They're just basically a place where there's zero probability for the electron to be. Like it says, there's not much chemical significance to it. It's just interesting. In terms of whether it's important, the angular nodes, which we talked about in the last video, or we had in the last video, they have some more importance in terms of chemistry, mostly because they dictate partly the shape. Shape dictates how bonding occurs and so forth. And so if you look at these plots, you also have, you can figure out the highest probability based on the maximum radial distribution function. And if you look, so in the first one, you can see 1s has the shortest, it's the smallest orbital. It has the smallest radial distribution. And then the 2s, it's a little larger. You can see it's out farther. But what's interesting is if you look at the 3s versus 3p, the highest probability in the 3s is actually farther from the nucleus than 3p. And so now we have all of these wave functions, these radial distribution functions we can look at. Then we ask the question, are the wave functions an eigenfunction of R? So we wanted to measure, okay, where is this electron with respect to the nucleus in a hydrogen atom? If it were an eigenfunction, we would just operate and return the eigenvalue. But of course, we know nothing is an eigenfunction of R. And so we have to determine an expectation value. And so the complete wave function expectation value is a triple integral. We're going to have the theta and phi dependence as well. But the radius isn't really impacted by the angular part. That's how we actually solved it to begin with. We can separate them. So we can simplify this radial distribution function, or this expectation value, excuse me, in terms of the radial functions. And so let's try to work through this in a PowerPoint slide and see how this works in terms of our expectation value. So I have it set up for the 2s orbital, and here is our radial. This is, if you go back a couple of slides, we had that particular radial distribution function, or excuse me, radial function. And then we have the r cubed dr. Now the r squared comes from the volume element, from the d tau overall. and the r comes from our operator. Okay, so that ends up being an r cubed. And so we then multiply this out, and we pull out the constant. Sorry, so we've got 1/8 and 1 over a0 cubed out front. We've now got the new integral, and if we multiply that through, we end up with, if you distribute, you square what's in the parentheses and distribute into 3 different integrals, which is what I've done here. We set them up. Now each one of these integrals are in a form that we can find in our table of integrals, I think on page 11 in our text, but you can also find them in other places as well. And so then that gives us this integral. So these are 3 factorial over, 1 over a0 cubed, or fourth on the first one, and so forth. And so you see the 3 terms that you get. If you multiply those out, almost all of the a0's go away, and we end up with 6 a0. So it's 6 Bohr radii is our expectation value. So if we were to do this measurement multiple times, the average would be 6 Bohr radii. So 6 times 52.9, whatever that ends up being, 300 picometers or something like that, for the 2s orbital. So that would be where we would find the electron if we measured it lots and lots of times. So if we went, so let's see if we did this. So at this point, we've just used the radial function. What if we did the whole triple integral for this expectation value? Can we get the same answer? And we should, but I want you to try that and see if you can. And until next time.